Alright, so welcome back to Particle Physics and the Standard Model. This is lecture 53, and last time we started studying the phenomenon of decays, right, which we saw could just be thought of as 1 to n scattering as far as getting the expression for the rate goes from the amplitude and the Lorentz invariant phase space, right. And from there on we thought about various channels of decay, and that gave rise to the notion of branching fraction, and we saw that the branching fraction could be the unique identifier of a particle, which is just how the Higgs boson was discovered recently, right. And then we saw some subtleties about how to get the decay rate from Lagrangian parameters, and in particular if the coupling constant was a dimension full quantity with positive dimensions, positive mass dimensions, then at the end of the day you are going to get a decay rate that looks like this, right, where you have the coupling constant squared, which is always there in the amplitude squared, but to compensate for the dimensions you have the mass of the mother in the denominator over here, and you always have a term that accounts for the phase space available for the final state. Okay, if the final state masses, the sum of the final state masses is close to the initial state, then you are not going to have decay. Then we saw the reverse case also with the example of muon decay, where in the Lagrangian, at least at the effective level, if you write down the Lagrangian as a contact operator like this, then the coupling constant out there has negative dimensions, basically negative mass dimensions. In this case it is nothing but the Fermi constant, which is 1 over v squared, where v is the Elter-Weak scale, right. Now again in the decay rate, because you are squaring the amplitude, you will get a gf squared, but now to compensate for the dimensions you will have positive powers of the mother's mass in the numerator as opposed to the denominator, right. So that is what determines all these things go into determining the decay rate, and we saw that with just this simple prescription we were able to get a muon lifetime that is very close to what is being measured, because we did not put in the correct phase space, but that is okay, alright. So let me start this lecture with a quick question that I had just touched upon last time. You can think about this and answer for yourself. Is the decay rate Lorentz invariant? We saw earlier that the cross section was not Lorentz invariant, right, physically it did not make sense, and then we saw that by looking at the ingredients in the expression for the cross section we saw it was not Lorentz invariant. What about the decay rate? Of course the decay rate is also not Lorentz invariant, right, it is related to the lifetime and all that, and in particular from this expression you separated out a Lorentz invariant term, which is the Lorentz invariant phase space, right, d ellipse. Then what you are left with is the amplitude squared divided by the energy, but it is just the energy, right, I did not write down like the invariant mass or anything, the energy of the initial state, right. So it depends on the frame that you are talking about, okay, that stands to reason, right, it is a rate after all. So and rates do differ according to the inertial frame that you are measuring them in, right. So let me just write that down quickly. Decay rate also not Lorentz invariant. Okay. So today we will see another way of thinking about and measuring these decay rates, by which I mean previously in the case of muon decay for instance, we got the lifetime to be about 2.2 microseconds, right, a few microseconds. What does that mean? It means you can literally, if you have a timer that is fast enough, you can literally measure the time it takes for the muons to disintegrate, either by looking at the disappearance of the muon or by counting the or by registering the appearance of the decay daughters, or a combination of both, right. So you can literally actually do it with a sensitive enough instrument, right. But what if the decay turns out to be pretty long? Okay. By pretty long I mean not just minutes or hours, let us say years. Okay. Will you keep waiting around for a year or 10 years or 100 years, generations to look for the decay of a particle? That is not a practical way to do it, right. What you do instead, okay, for long lived particles, right, you would basically assemble a large number of them. Okay. So, what is the advantage of that? After all, the decay rate does not mean that all the particles decay at exactly that moment, right. It is not like all the muons will decay at exactly 2.2 microseconds. This corresponds to the half life, right. What is the half life? If you started with some n0 number of particles, then after the decay lifetime or the half life if you want, you are left with n0 times 2, right, because ultimately all of this comes down to an exponential depletion of the particle population. Remember all this from high school, correct. So, if you want to study long lived particles, instead of waiting for one particle to decay, take a large number of particles and see if some of them decay, and from that from the it just comes down to from the number of particles in your sample as a function of time. By fitting this curve you can get the decay rate or the lifetime. Okay. So, let us apply this idea to one class of experiments that is already being done, it is being pursued actively. Let us just apply this idea to proton decay. Do protons decay? Not in our lifetimes, but remember in the very first class or in the third class or something I said protons are protected by baryon number, but baryon number is not an exact symmetry. So, in the Standard model the lifetime of the proton, if I am writing this correctly, is about 10 power 137 years, correct, which is a very long time. The universe has been around only for 10 power 10 years, right. But in theories beyond the Standard model, usually written as BSM, right, the proton decay rate could be much smaller than the proton decay rate in the Standard model, which is 10 power 137 years. Okay. There are many such theories, especially involving things called grand unification of forces and all that, but you can write down any number of theories for proton decay. Okay. And one typical channel for proton decay is a proton disintegrating to a positron and a pion. Okay, it is kinematically possible. You can violate baryon number and lepton number and get this final state. Okay, this is one example, people do look for this. Okay. So, how do we have not seen it, but by assembling a large number of protons like this, we can at least try to set a limit on the decay lifetime of the proton. Okay. So, let us do this step by step. What people do consider for these things. Okay. Let us do this in 3 rounds. Okay. Let us start with a very simple round. Okay. If you did not know anything about anything else about proton decay, or if you did not know anything about how experiments are set up, there is still one thing you can guess about the lifetime of the proton. It should be larger than the lifetime of the universe, right. We know that protons have been around since the beginning, at least since Big Bang nucleosynthesis, which is in the first few seconds of the universe. So, must be, and protons have been around until now. So, clearly it should be at least greater than the lifetime of the universe. And what is that? It is basically 13.7 billion years. Okay, I am just going to write it as 10 power 10 years. Okay. Now, let us go to something more non-trivial. Now, before anybody set up a real experiment to measure proton decay, there was a very interesting and very neat estimate made for the lifetime of protons due to an experimentalist called Morris Goldhaber. He said, tongue in cheek, he said, we know it in our bones that protons do not decay within 10 power 17 years. Okay. So, what did he mean by that? He meant if protons do decay like this, okay, suppose this happens, then you have positrons in the final state. That would mean that in your own body, right, we are all made of protons, correct? In your own body, you will be making all these energetic positrons. A proton is a GeV in mass, right? So, this is a GeV, this is just 100 MeV, right, and this is like 0.5 MeV, right. It means you are almost dumping all this GeV energy into the positron, like 90% of it goes into the, 50% of the proton mass goes into the kinetic energy of the positron. So, these are very fast positrons, right. So, your body itself will be producing these positrons so much that it will give off all this ionizing radiation, okay, which will end up giving us cancer. Okay. So, the body itself gives itself cancer this way if protons were to decay too fast. That is the idea that he made use of. Okay. And the fact that this does not keep happening can give you a minimum lifetime for the proton. So, let us do that calculation. Okay. It turns out the lethal dose of radiation, all right, is about order 1 sievert. Does anyone remember or know what the sievert unit is? Sievert is nothing but 1 joule of radiation, okay, dumped into 1 kilogram of tissue. Okay. So, if it turns out for over some period of time you got 1 joule of radiation from some radioactive source in just 1 kilogram of your tissue, that is already a lethal dose, that is enough to kill you. Okay. So, Goldhaber made use of this. This lethal dose was known in his time, I believe this was 60s or 70s, and he simply calculated that since we all live 100 years, 10 to 100 years, right. So, order 10 years, right. So, he made use of that fact and said that if the rate, right, the total rate of decay, let us call it that, of proton decay, okay, has to be smaller than, in the denominator I am going to put, we all live order 10 years, right. So, I am going to put order 10 years, okay, and this is the fraction of protons that have to decay in your body, right. So, that would mean what is, so 1 joule of radiation would mean I need 1 joule of energy from protons. Okay. Now I just said that half the energy, you can even say that even the pion will go and actually produce radiation ultimately, because the pion also decays to 2 photons, right? The pion decays to 2 photons. So all of this is radiating, all of this is radiation, I am sorry. At the end of the day, all of this is ionizing radiation, right? So the entire GeV mass of the proton goes into radiation. Okay. So that means in the numerator, I can ask for 1 joule of protons, for 1 joule of radiation, how many protons am I thinking about? Okay. And for that, I am going to give you a unit conversion. 1 joule is about 10 power 10 GeV. Okay. Now, proton is around a GeV, right? That means that corresponds to 10 power 10 protons. So that is the energy. Now, this has to be dumped into 1 kilogram of tissue, right? So, we are asking what fraction of your tissue is producing this 1 joule of energy, right? So, to get that fraction, I need to know how many protons are in 1 kilogram. Okay. So, what is that? You can go use the concept of a mole and all that, and you will find that whatever it is at the end of the day, to the correct order of magnitude at least, it will be 10. So, it is like Avogadro number, which I am going to just take it as 10 power 24. Okay, we are just calculating orders of magnitude here, right? That is the Avogadro number, and that is for a gram, this is a kilogram. Okay. So, that is a kilogram, and that would correspond to, as I was saying, 10 power 27 protons. Okay. Now, I am going to use that here to see that the rate, which depends on the fraction of protons that are disintegrating, has to be smaller than 10 power 10 divided by 10 power 27. Okay. Now, what is that? See, let me just mark this here. So, this bit is this. This is your lifetime. Okay. So, each human is their own source as well as their own detector in this experiment. Okay. So, that tells me simply that the rate of proton decay from this consideration is less than 10 power, this is minus 17 and minus, there is a 10 in the denominator, order time I will just take it as 10 right now. Okay, your inverse, or said differently, the lifetime of the proton is larger than 10 power 18 years. See, just like that, without much effort, we were able to set a limit on the proton decay lifetime, just based on the fact that we are not getting cancer from our own tissue, from our own bones and tissue. Okay. Now, what is the age of the universe? To compare this, the age of the universe is 10 power 10 years. See, although the protons live much longer than the age of the universe, just by assembling a large number of protons into human beings, we are able to set a limit on the proton lifetime that is much larger than the age of the universe, right? Very good. Of course, this is not the best way to set a limit. Even more impressive limits can be set by putting protons in a tank. Basically, take some liquid. What is the best liquid? Water, right? So, take water in a tank and then attach some say photomultiplier tubes, okay, What are photomultiplier tubes? These just pick out a single photon, right? If you are in a really dark place and you put photomultiplier tubes, this can pick out even a single photon if it hits the tube, if it hits that detector, right? So PMTs, how do they do that? They convert that to a photoelectron using the photoelectric effect. Okay. So this you can do. You can take a large tank or vat of water, go underground so that you don't get contamination from cosmic rays and so on. Okay. Put it in a very dark place and look for the proton decaying. If it decays to say E plus pi 0, you know that the pi 0 will produce 2 photons, right? But also the E plus will be moving very energetically. In particular, it will be moving at relativistic speeds, right? So all of this will give you Cherenkov radiation, because you will have light moving faster than, you will have exactly photons moving, the particles moving faster than the speed of light in that medium, right, in the water medium in this case. And you can pick out the photons coming from the Cherenkov radiation in the PMTs. Okay. This is the principle of the leading experiment in this business called super Kamiokande. I have just described the essentials of that experiment, okay, in Japan. Okay. And the super Kamiokande people have set the best limits on the decay of the proton. So how did they do that? Again, the principle is the same. Okay. They have, they are thinking about, or rather they actually have in their experiment 22.5 kilotons of water. Okay. How many protons is that? Let's calculate it. So 22.5, right? So let me just take it as 20 times, I said kilo, so that is 10 power 3. Ton is 10 power 3 kilograms, right? Now I had kilograms, so I put one more 10 power 3. So kiloton means there are 2 kilos sitting in it, right? Then finally grams. Grams is what? 5 times 10 power 23 protons. That's Avogadro's number, roughly. Okay. So what is this? This is 2 times 5 is 10. Okay. Then I have 1, 3, 3, 3. So that's 10 power 10. And then I have 10 power 23. Right. So basically this is 10 power 34 protons. Okay. Now all they have to do is wait for one of these protons to decay. And typically these experiments last for a year. They actually, this time this is, I think it's lasted almost 10 years if I'm remembering correctly. But let's just say the typical time scale for an experiment like this is a year. Okay. If that is the case, then if you haven't seen a single proton decay and give you Cherenkov light that can be picked up in PMTs, you can confidently say that the proton lifetime is smaller than 10 power 34 over a year. That simply means you set a limit on the proton lifetime of 10 power 34 years. Okay. So I'm going to put a squiggle because these are all approximate values. Depending on exactly what the final state is and the experimental sensitivity to that final state and the analysis made for that final state, though these numbers differ a bit, but they are all around this order of magnitude. Now look at this. This is such an impressive number, right? 10 power 34. We've only been around for 10 power 10 years. the entire universe, but then we have already setting a limit of 10 power 34. Actually, it's 24 orders of magnitude farther away from where we are. But this is what we can do with these sensitive experiments, and see, we can calculate this without much effort. Just count the number of protons and look at the time that you have. Okay, so this is the other way of measuring lifetimes for long lived particles. Okay, so I am going to close our discussion on decays with a very, to me it is a very interesting bit of particle physics that illustrates the very deep relation between relativity and particle physics itself. Okay, and with that I will also wrap up the lecture before moving on to other things. Let me preface this with basically the dimensionality. I am going to write what I am going to talk about first, and then I will tell you the dimensionality of time and particle decays. Why are these two things related? How are these two things related is what we are going to see now. Okay, the fact that we have only one dimension of time is very deeply related to a property of particle decays. Okay, and let us begin the discussion with the following observation. Okay, I am going to draw a space-time diagram. Okay, if you want, you can go and brush up your special relativity and in particular go think about space-time diagrams. And I am just drawing a space-time diagram in two-dimensional space, and this is the null vector at 45 degrees, correct? And I am going to start by considering a time-like vector. Okay, starting from the origin, I have a time-like vector with this direction and this magnitude. All right. Okay. Now, what is the length of this vector? I can write it this way, right? I can use this as the metric, or rather the space-time interval. I can write, let me write it in blue. This is dt squared minus dx squared. So, I am writing it for in an infinitesimal form, but of course, you can integrate it to get the actual length. Okay. So, this is the Minkowski space, right. So, I am going to ask now, if I were to bend this vector this way, okay, or said differently, if I went from the origin to the edge not by a straight line on the space-time diagram, but through a bent line like this, okay, I am going to ask, is the red vector longer or shorter? You can pause your video to think about this. Okay, obviously it's not, the answer is not going to be obviously longer. It looks longer on this diagram, but remember we are talking about Minkowski space, it is not Euclidean space. Okay, the answer is not so trivial. So, you have to think about it and try to come up with your answer. Even if it is wrong, it is alright. Try to come up with your own answer for this question. Okay. Now, I am going to give you the answer, but I hope you already thought about it. The answer is, it is shorter, and I will tell you why. Because when I draw this line, I am actually, can you see the arrows that I am drawing here? I am actually distorting this vector in a direction that is it in the direction that is it time like or space like. So I am just drawing these perpendiculars, right. I am drawing all these perpendiculars to the green line, to the time like vector. So if I draw something perpendicular to the time like vector, is it space like or time like? It's obviously space like, right. So look at this. This orange arrow I am drawing is parallel to the other orange arrows, right. That is, this orange arrow is perpendicular to the green arrow and hence it is space like, correct. So what does this show? It shows that if I make space like this time like arrow, basically I have made space like bends around it so that this is increasing, this bit is increasing, right. If that is the case for the red arrow, right, let me write it in black now, the red one is actually shorter. You agree? dt square is still the same, but in dx square I have increased the dx square component, so I have made the arrow shorter by doing this bend. So for this class I am going to stop right here and I want you to process this, alright, and think about other kinds of bends that you can make to this arrow, and go ahead and draw a space like vector and bend that arrow also and ask yourself whether those are longer or shorter. So in the next class we will take that question up and see how it is related to particle decay, alright. Okay, see you in the next class. Thank you.